Oh, no, I didn't. No, seven. You guys
All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Doing good. I'm sure things are probably getting busy for you guys this semester. Midterms coming up. Speaking of midterms, we do have a midterm in this class coming up, so it's going to be next Thursday. So it's Thursday, March 6th. So some information about the midterm exam for you guys. First of all, the format of the exam. You can expect to see the 4 short answer questions on the exam. So those are going to be conceptual questions that you're going to answer with maybe 2 or 3 sentences. Maybe I'll have you draw a picture or something. So that's going to be worth 40% of the grade. So that's very similar to kind of how the homeworks are. And as for the other parts of the exam, you can expect anywhere between somewhere between 5 and 6 problem solving questions. And so, for this first unit, it's pretty straightforward. I'm going to give you an ordinary differential equation, maybe homogeneous, maybe non-homogeneous, maybe with step functions, maybe with not. And you'll solve those, and that'll be worth 60% of the points. Okay. The amount of questions I end up putting is going to depend on the length, and so usually what I like to do is I always take the exam. I write the exam, I take it just to make sure that timing is not an issue. So if I do see that the time's going a bit long, then I'll come down to 5. Okay. In terms of what you can bring for the exam, so at the very least, you'd bring a writing utensil, bring a calculator too. I don't think you'll need the calculator, although it's good in case you are doing some heavy arithmetic, just to kind of help speed that up. In addition, you can also bring one 8.5 by 11 sheet of notes, and so that's kind of a standard printer paper size, and you can use both sides of the sheet. Okay. You can handwrite it, you can type it, you can put whatever you want on it. The only thing you can't put on the cheat sheet are the answers to the exam, but that's gonna be very difficult unless you can read my mind or hack my computer. So please don't do that. Just kind of put what you want on the cheat sheet. Strategies for the cheat sheet. So I've seen, I've been teaching for about 6 years now. I've seen a variety of different strategies with the cheat sheet. I've seen some people take all of my lecture notes and just make them really small and just kind of print them all side by side on the cheat sheet. And that is certainly a strategy. I wouldn't say it's the recommended strategy because, in those cases, what I see is people spend more time looking at their cheat sheet trying to find the answer rather than taking the exam itself. And then, you kind of run out of time, and then you don't really get to the parts of the exam that you want to. So, my recommendation for the cheat sheet is, really kind of take your time making the cheat sheet. We've gone over a lot of information in this first 6 weeks of the semester. And an 8.5 by 11 sheet, maybe that's a bit more than what you've gotten for some of your other classes, but it's still not that much space. And so kind of the exercise of taking all the information that we've learned, condensing it down into just a single sheet of notes that you can bring to the exam. Just that process of taking all the information, processing it, condensing it, that by itself is already a great tool. And what I've noticed that the people that really put a lot of effort into their cheat sheets, don't actually use it all that much during the exam. They can use as much time as they want to actually take the exam, and they end up doing a lot better. Okay. I've also seen people just, kind of fiercely trying to write their cheat sheet like in the 5 minutes before the exam. So again, that is a strategy, but probably not the best strategy. Okay. In terms of content, so there's going to be 3 homeworks that are on the exam. Question in the chat. So please don't particular on the exam. Also, you have to turn in the cheat sheet too. So I'm not going to collect the cheat sheets. I used to, but just as I've kind of done this job more, I've procrastinated more and more in writing the exam. And so, there's less concern that I have of people actually getting the exam answers beforehand. So I don't collect it. You can expect a particular solution on the exam. That was a big part of what we covered so far. So you can expect at least one question on that. But I do realize that those questions are more time consuming, but you can expect at least one. So in terms of the content, homeworks 1, 2, and 3 are definitely great to study for the exam. So that's going to cover basically, our first part of the semester here has been kind of broken into 3 parts. We have first order ODEs, second order ODEs, and then Laplace transforms. And so, that's homeworks 1, 2, and 3. So I would definitely study those. The way I would study those homeworks is, not just to look at the solutions and to actually just try to redo the problems yourself. By the way, I am going to post the solutions for homeworks 1 and 2 this week. And then homework 3, I'll probably post a solution for that early next week. And then another handout I'm providing you guys is a study guide. So if you go on the Canvas site, you go under week 6, there's an additional PDF. I actually just posted it just about an hour ago. It's a study guide for the exam. So the study guide kind of gives you a nice overview of everything that we covered. The study guide is actually really useful for the conceptual questions. So for the 4 short answer questions, I would definitely check out the study guide, because that one kind of overviews all of the concepts that we've gone over. And so that's definitely a great resource for you to check out as well. Okay. All right. Any questions on the exam, or just any questions about anything in general? Yes.
I don't know if we covered this, but is there gonna be nothing on the exam, for example, like Laplace transform table, or is that all?
Oh, thank you. Thank you for reminding me. I will provide the Laplace transform table. So you don't need to put that on your cheat sheet.
Okay,
Yeah.
thank you.
Yeah. Thanks for reminding me. Mhm. Let me write that down. Sure. I think the question in the chat was kind of just that exact same thing. So I did post some additional examples on Canvas. So I think I posted some additional Laplace examples and additional step and impulse function examples. So I would definitely check those out. Just kind of the more practice that you get with this material, I think the better. Those examples, I kind of have them just in case we have extra time in the class to go over them. But I didn't have that much time this time, but I would definitely check out those examples to give you some more practice. Questions?
Yeah, and then are we also gonna get the table for the other problems with, for the differential equations? It's like the form of R of X, and then, yes.
I can provide that too. Yeah, I'll go ahead and add that to the Laplace table too.
Thank
Yeah.
you.
Mhm.
Was it like this entire page? Like it was like,
Exactly. Yeah.
okay, so this will be.
Exactly. Yeah. So I think that one does have the particular.
Yeah.
Okay. Yeah. I'm just gonna print out 35 of them. Just give it to you. Right. Any more questions on the exam? Okay. All right. And so so up until next Thursday, there's a lot of office hours. So I have office hours Thursday, I have office hours next Monday and next Tuesday. And if you have any very, very last minute questions, I do have office hours the hour right before the exam. So you can come and ask that as well. Okay. Okay. So let's go ahead and pick up where we left off. And so I do expect us to finish all the Laplace stuff by the end of this week. And so after this week, then you won't have to worry about anything new being on. All right, so when we left off last Thursday, we were talking about, we were kind of starting our discussion about step and impulse functions. But in particular, we were looking at what I call the second shifting theorem of Laplace. Okay. And so kind of the informal name for the second shifting theorem is a T-shift. Okay. All right. So because Laplace is an integral transform and it involves an exponential, whenever you multiply a function by an exponential, either in the physical domain or in the Laplace domain, it usually implies some kind of shift of some kind. Okay. So we've gone over the first shifting theorem. So the first shifting theorem basically states that if you multiply a function by an exponential in the time domain, physical domain, that's going to end up being a shift in the Laplace domain, right? So the second shifting theorem is kind of the opposite. So basically, if you multiply if you multiply a function in the Laplace domain by an exponential, what that's going to do is that it's going to end up shifting your function in the time domain, in the physical domain. hence the name t-shift. All right, so the kind of the concise form or kind of the concise mathematical form for the second shifting theorem looks like the following. And so if you have some function f of t in the time domain, okay, or the physical domain, that should be consistent. So if you know a function f of t in the physical domain, and you know its Laplace transform to be big F of s, okay? So big F of s is the Laplace transform of f of t, then if you take e to the minus as times f of s, right? So you take that same Laplace function and you multiply that Laplace function by e to the minus as. That's going to cause a shift in the time domain. Okay. And so what this is going to be the Laplace transform of f of t minus a multiplied by the step function u of t minus a. Okay. So, once you kind of get used to doing these types of problems, if you see yourself getting, if you see a function getting multiplied by an exponential, then, it should start to trigger some bells in your brain. All right, I'm probably going to see a shift in the opposite domain on the other side. Okay. So second shifting theorem is if you multiply by an exponential in the Laplace domain, then you get a shift in the time domain or the physical domain. Okay. All right. So this is really useful for cases when you want to shift starting point of a particular function. Okay. So let's do an example to kind of see how this is used in practice. Okay. So the most common case that you're going to see this shifting theorem and these step functions and impulse functions are going to be situations where you have a discontinuous function that you want to model. Okay. So for example, let's do a very simple case first. So let's say we have f of t, right, is equal to. So this is going to be discontinuous, and so this is a common way to show kind of discontinuous functions, where the function is going to take different values depending on the value of t, or depending on what time it is. Okay. Okay. So for example, let's say that f of t here we want it to be 0 when t is less than 0. Let's say that f of t is going to take the value of t when t is greater than 0 but less than 5. So our function is going to be active between 0 and 5. And then we're going to turn the function off again when t is greater than 5. Okay. So this is a very simple case of what we call a discontinuous function, where its values are discontinuous. There's not just one smooth function throughout the entire. Okay. So if we plot this, just so you can kind of visualize it, it looks like the following. Okay, so when t is less than 0, so when we're on the left-hand side of the vertical axis, then our function has a value of 0. Okay. And so it's a little bit hard to draw just because it's going to overlap with the horizontal axis. Okay. So over here basically says that f of t is equal to 0 when t is less than 0. Okay. Next, we have the regime between 0 and 5. So between 0 and 5, our function is going to take the value of t. And so t is just a linear function, just like that. Okay. And this is going to continue all the way up until t is equal to 5. Okay. And then after t is equal to 5, then our function is going to shut off yet again. And so at this point, it's going to be 0 again. Okay, so visually that's what our function looks like there. Okay, so discontinuous, only active in that short time frame between 0 and 5. Okay, so when you have a discontinuous function like this, usually there are two things that you want to do. Okay. So first thing that you want to do is that we're gonna first represent this function using using step functions. So we're going to represent the discontinuous function f of t as one single expression using step functions. Okay. And then the second thing that we're going to do, once we have that representation or once we have that expression from part 1, is we're going to take the Laplace transform of that expression. And in that case, we're going to utilize our second shifting theorem in order to apply some shifts. All right, any questions on the setup for this example here? Okay, good. All right, so let's go ahead and do this. And so, for this problem, we have a fairly simple case. The function is really only active in this small window right here. Okay. And so let's just focus on that, because outside of this window, f of t here is just going to be equal to 0. So we don't need to consider it. Okay. Okay, so let's do part 1. Function only active between t is equal to 0 and t is equal to 5, right? All right. In fact, another way that we can kind of describe this is that the function is turned on, or it's flipped on at t is equal to 0. And then after t is equal to 5, the function is then flipped off, and so it goes back down to 0. I try to avoid saying something sus by saying I didn't want to say turned on because that's weird, but then I end up saying flipped off, which is also not good too. So. All right, but you guys get it. Okay. Anyway, all right. So let's first thing we're going to do is we're going to represent this using a square wave. Right. So remember, square waves was a concept we went over last time. Basically, if you have a function that is turned on and turned off at a certain point, we can represent that with 2 step functions. Okay. Okay. So the function is flipped on at t is equal to 0, right? So that means we're going to multiply our function by u of t. Okay. because u of t is a step function that starts at t is equal to 0. Okay. And then to turn it off at t is equal to 5, we're going to subtract another step function, but this one's going to be delayed. So it's going to be a step function that's offset by 5. Okay. So the factor that we have here is u of t minus 5. Okay. And the function that we are modifying here is t. Because that's the value of that function in that interval. Okay. And so this is part 1 of the problem. So we have f of t is equal to t multiplied by step function u of t minus u of t minus 5. All right, so that's kind of what it means to represent a discontinuous function with step functions. And so you basically have to look and see when the function becomes activated, when it becomes deactivated, and then you add and subtract the appropriate step functions, according to that. Okay. All right, any questions on how we got this result here? Okay. All right, so that's part 1 of the problem. Part 2. Let's take the Laplace transform of this expression. Okay. All right, so to take the Laplace transform, first thing I'm going to do is I'm going to distribute t throughout the entire to both of these terms here. So f of t is equal to t u of t minus t u of t minus 5. Okay. Then let's take the Laplace transform of this. All right, so we're take the Laplace transform of f of t. So that's going to be the Laplace transform of t u of t minus Laplace transform of t u of t minus 5. Right. Just making use of that linearity principle of Laplace transforms. Okay. So we have 2 terms here that we need to take the Laplace transform. So we have t u of t. So this one's actually no problem. So this one actually just becomes 1 over s squared. Okay. Because even though we're multiplying by a step function there, the step function there doesn't actually have an offset. So and so in that case, we can just take the Laplace transform straight up. Okay, so when the step function has no offset, so there's no u of t minus something, it's just u of t, then what we say is that the function has no offset, so there's no shifting required. Good. Now the second term. So the second term, we do have a shift. So in this case, our step function is actually shifted by a factor of 5. Okay. So we are going to need to apply the second shifting theorem here. Okay. But we need to be careful when we're applying this, because if you look at this, then this function actually doesn't have the same, this function actually does not have the same, the value of t is different inside and outside of the step function. Okay. So in this sense, the second shifting theorem is a little bit more complicated to apply than the first shifting theorem, because you have to make sure that the shifting is kind of matches in between the two. Okay. So in other words, this shift inside the step function has to match the shift of the function that's multiplying. Okay. And right now they're mismatched, so they don't have the same shift there. Okay. Okay, so what can we do? So we need to kind of modify this function here in order to match that shift. Okay. So in order to modify that shift, we're going to make use of we're going to make use of the second shifting theorem, but we're going to make use of a slight modification of it. Okay. So this is the same second shifting theorem. It's just that we're kind of moving the terms around a little bit to make it a bit more convenient. Okay. So you can derive this this version here from the original one. It's just this is just more convenient to apply in situations like this. Okay. Okay. All right. So the modified version looks something like this. So let's say that you want to take the Laplace transform. Well, first of all, it's you have to assume that you know the Laplace transform of f of t. Okay. So if Laplace transform of f of t is equal to f of s. Okay. Right. So that's kind of the starting point for all of our shifting theorems. Okay. All that basically says that you have the Laplace table and you can take the Laplace transform, no problem. Okay. So if that's true, let's say that you want to take the Laplace transform of f of t multiplied by a shifted step function. Okay. So that's exactly the case that we have right now. So we have a step function with the shift multiplied by a regular kind of f of t that doesn't have a shift. Okay. This mismatching shift. Okay. Okay. And so in those cases, the way to take the Laplace transform is to first multiply the entire thing by e to the minus as. And so that you do need to account for that e to the minus as on the front. Okay. So this e to the minus as is going to account for that shift in the step function. So there's our second shifting theorem at work. And so we have a shift in the time domain. And so that's going to end up being an exponential in the Laplace domain. Okay. But the way that you adjust for this is that you apply kind of the opposite shift to f of t. Okay. And so in other words, you're going to multiply this by the Laplace transform of f of t plus a. Okay. So with this right here, we're going to apply kind of the opposite shift to our function. I know it's kind of a lot. And so I think we spent a bit of time last Thursday saying that if you're doing first shifting theorem, the sign reverses. If you're doing second shifting theorem, the sign stays the same. But if you're using the modified second shifting theorem, then the sign reverses again, actually. So you end up with kind of a positive shift. It's a lot to take into account. But then I think once you start doing some examples and you start to see the context of when you apply these things, I think then it becomes a bit more make a bit more sense. Okay. So the context for applying this modified version of the second shifting is usually when you have a discontinuous function that you want to take the Laplace transform of. Okay. So that's usually the context. Outside of this context, I don't really use this version of the second shifting theorem all that much. But this is kind of a very specific, but also kind of fairly common way to use this. Okay, because eventually what we're going to do is we're going to be using these step function and impulse functions to modify to basically apply these as forcing functions to our ordinary differential equation. So kind of like the situation we talked about last time. You have a circuit, you have a switch, you can flip it on, you can turn it off. You'll have basically a discontinuous forcing function, and this is where you would apply something like this. Okay, any questions on kind of this modified version of the second shifting theorem? Okay, all right, so let's see it in action. And so if we apply this to this example, okay, so let's kind of remind ourselves what this example was. And so for this example, we're taking the Laplace transform of t times u of t minus 5. Okay. So this is kind of a perfect chance to apply this modified version of the second shifting theorem. Okay. So let's take this, let's multiply. So the shift is 5, and so we're going to multiply by e to the minus 5s out in front. Okay. And then let's take the Laplace transform of our function, but we're going to apply the opposite shift. Okay? And so instead of taking the Laplace transform of t, we know that our shift is 5. And so we're going to take the Laplace transform of t plus 5. And then the e to the minus 5s, we can just kind of ignore that for now. Okay. But what we have here is just we have the Laplace transform of t plus 5. This is a fairly easy function that we can do. Okay. So let's break this up. So we have e to the minus 5s. It just kind of comes along for the ride at this point. And so we have Laplace transform of t plus Laplace transform of 5. Okay. And so we can do both of these from the table. And so this is Laplace transform of t, we know, is 1 over s squared. And Laplace transform of 5 is 5 over s. Okay. Okay, so let's go ahead and multiply that through. And so this just ends up being e to the minus 5s all over s squared plus 5e to the minus 5s all over s. Okay, so let's combine that with our previous results. So if you remember kind of, about 15 minutes ago, we had the t u of t term there as well. Okay. And so the Laplace transform of this function f of t, okay, which is our discontinuous function, was 1 over s squared plus e to the minus 5s over s squared plus 5e to the minus 5s all over s. Okay. Okay. Any questions on how we got this result here? Okay. All right, let's do one more example of this, just to get some more practice. All right, this will be a bit more complicated, and this one actually will that modified version is going to play a role again. Okay. All right, so let's have f of t is equal to 2 when t is between 0 and 1. Okay. It's going to have a value of 1/2 t squared when t is between 1 and pi over 2. And then after that, it's gonna have a value of cosine of t when t is greater than pi over 2. Okay. Okay, so same thing we did in the last problem. Let's first represent this as one expression using step functions. Okay. So we're going to make note of all the different parts of this discontinuous function and just, activate them, deactivate them according to the times listed there. Okay. And then step 2 is we're going to take that expression and we're going to take its Laplace transform. So I probably won't take the Laplace transform of the entire thing just because of time constraints, but I'll do the first few with you just to get you some practice. Okay. Okay. So let's do step 1 first. So let's represent this entire expression using step functions, right? So we have 3 parts here. So we have 2, okay, which is simple constant values. So this 2 is activated at t is equal to 0 and then deactivated at t is equal to 1. Okay. So it's going to be 2 multiplied by u of t minus u of t minus 1. Next one we have is 1/2 t squared. So we have 1/2 t squared. This is going to be activated at t is equal to 1. So we're going to multiply this by u of t minus 1 minus u of t minus pi over 2. Okay. And then finally, we have cosine t. So we have plus cosine of t. And this is activated at t is equal to pi over 2. So multiply by u t minus pi over 2. Okay. All right, so let's go ahead and distribute these through, just so that, we don't have, we can kind of see every term equally. Okay, so after we distribute, we get f of t is equal to 2 times u of t minus 2 times u of t minus 1, okay, plus 1/2 t squared u t minus 1 minus 1/2 t squared u of t minus pi over 2 plus cosine of t times u of t minus pi over 2. Okay. So all I did was I just took each expression there at each function and multiplied it by their step function. Okay. Okay. All right, so we have a lot in Laplace here. So there's actually 5 different expressions here. So we have 2 terms with 2 terms with 1/2 t squared, and 1 term with cosine t. Okay. Okay. So let's take the Laplace of this expression. All right, so luckily the first 2 terms here are fairly straightforward. So those are just constant functions. Okay. So first we have 2 u of t. We know the Laplace transform of this. This is just going to be 2 over s. Okay. Next we have a minus 2 times u of t minus 1. So this one does have a shift, but for a constant function, you actually don't need to apply any opposite shifts or anything like that, because a constant is just going to be a constant. Okay. And so this is going to be a minus 2. We're going to multiply by e to the minus s to account for the shift, okay? And we're going to divide that by s, okay? So again, even though that second term there does have a shift, for constant functions, you don't need to do anything special because constants are just constant. There's no t in them. Okay. Okay. Now all the rest of the terms here, we do have to do something a bit special for this. Okay. So let's do the 1/2 t squared ut minus 1 first. This might be the only one that we do because of time, because I do want to kind of move on. Okay. So let's do that one kind of on its own. So we have the Laplace transform of 1/2 t squared u of t minus 1. Okay. So this is very similar to the example that we had the last time. So we have a step function that does have a shift. And so the step function with a shift of 1 multiplied by a function that does not have a shift. Okay. So we have a mismatching shift between this and this. Okay, so let's apply our modified version of the second shifting theorem. Okay. Okay, so the modified version basically says states that we have a shift of 1, so we're going to multiply by e to the minus s. Okay. So again, this e to the minus s accounts for our shift. Okay. Then we're going to take the Laplace transform of our original function, but we're going to apply the opposite shift. So there's going to be the Laplace transform of 1/2 t plus 1 quantity squared. Okay. So we apply that opposite shift to that function. Okay. All right. So this problem here is a little bit different than the previous one, because the previous ones, once we did apply that opposite shift, we can just take the Laplace transform of that straight up. This one, unfortunately, we can't take the Laplace transform of this straight up because it's, t plus 1 quantity squared, which is not in our table. And so in order to actually take this Laplace transform, we first need to actually, FOIL this out and get a full quadratic expression. Okay. Well, first thing I'm going to take the 1/2 and just pull that out, just because that one's just a constant. Okay. So right now we have e to the minus s over 2 times the Laplace transform of. I'm going to take that t plus 1 quantity squared and just FOIL it out. And so that's going to be t squared plus 2t plus 1. Okay. So we can take the Laplace transform of each of these terms individually. So first we have a Laplace transform of t squared. So you have e to the minus s over 2 multiplied by Laplace transform of t squared is 2 over t cubed, or 2 over s cubed, excuse me. Then we have Laplace transform of 2t, so that's going to be 2 over s squared, plus Laplace transform of 1, which is 1 over s. Okay, so what started as a relatively innocent, straightforward function, 1/2 t squared times u of t minus 1, because of the shifting and because of how we apply the tables, it ended up kind of being a little bit of a monstrosity. Okay, so we have three terms with an exponential out. Okay. All right, any questions on how we got this result here? Okay, yes, question.
Is the first term in the parentheses, 2 over s cubed?
Yes, 2 over s cubed, yeah. Yeah, so Laplace transform of t squared. Question, yes.
So the explanation of A comes from within the parentheses.
Exactly, yeah. And so whatever shifted in the step function, that gives you your exponent on left. Yeah. Mhm. All right, question in the chat. So once foiled, then we just use the table of Laplace transform to get the solution. Yeah, that's exactly right. So the reason we foiled it is because, there's no Laplace transform of t plus a quantity squared. And so we needed to FOIL it out to get kind of these individual t terms. And then we can then use the table of Laplace transforms from. Yep. Mhm. Yep. Any other questions on this example here? Okay. All right, so that's how to apply the second shifting theorem in the forward direction. So that's how you apply to take the Laplace transform. But eventually, when we do solve our ordinary differential equations, we have to go backwards too. We have to be able to take inverse Laplace as well. Okay, so let's do an example of that. So let's take inverse Laplace. We're going to take inverse Laplace with the t shift. Okay, so let's say we have a function in the Laplace domain. So we have f of s is equal to 1 minus e to the minus 2s, all divided by s squared. And so we want to take the inverse Laplace of this, this function. Okay, so we actually have one term without a shift here, so we just have the 1 over s squared, and we have another term with a shift because that's e to the minus 2s. Okay, so let's break this up first. And so let's have one term. Let's have 1 over s squared, okay, minus e to the minus 2s over s squared. Okay, all I did was just kind of break it up into two fractions there just to make it a bit more clear. Okay, so this first term, we can take the Laplace inverse Laplace. This one's in our table, so there's no need to apply shift here. Okay, so this is going to be a function t. Okay. Whereas the second one, we do actually have a shift that we need to apply. Okay. Okay. So the good news is that, taking an inverse Laplace with a shift is actually a lot simpler than doing the forwards. And so, because you don't have to do any kind of weird plugging in, like you did from before. Okay. So here's my recommendation for doing these inverse Laplace with a shift. So whenever you see this, and you need to take the inverse Laplace, first thing I always do is I take the inverse Laplace of the base function itself. And basically we just and then just ignore the shift. Because every single one of these Laplace functions, if you just ignore the shift, should have a base function that is, that's applied to it. Okay. Okay. So for this function, we have an e or minus e to the minus 2s all over s squared, okay? We can see that our base function here is minus 1 over s squared. So what I'm going to do is I'm going to take e to the minus 2s. So I'm just going to ignore that for now. And then we're going to take the inverse Laplace of minus 1 over s squared. Okay. Okay, so the inverse Laplace of minus 1 over s squared, that's pretty easy. So that's just a minus t. Give you e to the minus 2s. Inverse Laplace of this is just minus t. Okay. Right. Then once you have the inverse Laplace transform of the base function, then you can apply the shift to it. And applying the shift takes 2 steps. And so first, every time you see t, you replace it with the shifted t. So in this case, it's going to be t minus 2. And you have to multiply it by the corresponding step function. Okay. So this is step B. Then apply shift. Okay. And once again, there's 2 steps of this. So replace t with t minus a, and 2 multiplied by a shifted step function. Okay. And so if we do that, we have a shift of 2 here. And so then we're going to have a minus t minus 2. Okay. So that's part 1 of this. So I took our function t and replaced it with t minus 2. And I'm going to multiply this by the shifted step function. So u of t minus 2. Okay. And so if we put it all together, we combine it together with what we had above. Then what we have is f of t is equal to t. And technically, it's implied that, any function by itself is multiplied by a step function, a non-shifted step function. But you can add it into if you're kind of OCD like me. Okay, so this is t times u of t minus t minus 2, u of t minus 2. All right, so taking inverse Laplace with shifts is a little bit simpler. You just take the inverse Laplace of the base function, and then you apply the shift on that. Okay. I know, today we're going over a lot of rules, a lot of kind of things, and it's hard. I know it's kind of hard to keep track of it all, but I think probably on Thursday we'll get to it. Thursday we'll actually apply these to solve some differential equations. We'll talk about impulse functions. I think things will make a lot more sense once we kind of put it all together. But just for this example, are there any questions on this? Okay. All right, let's do one more example of this, one that's a bit more complicated. Okay, so let's have f of s is equal to e to the minus s over s squared plus pi squared plus e to the minus 2s divided by s squared plus pi squared, okay, plus e to the minus 3s all over s plus 2 quantity squared. Okay. So we have quite a lot of shifting here. So obviously we have the t shifting because we have the exponentials in the s domain. But you can see here we have an s shift too. So that s plus 2 quantity squared, that one we're going to apply our first shifting here to. Okay, so let's take the inverse Laplace of these quantities here. Okay, so the first 2 terms are actually very similar. So I'm actually going to do these together. Okay. And so let's take the inverse Laplace of this. And so this is going to be inverse Laplace of 1 over s squared plus pi squared with a shift to them. Okay. So if we take the inverse Laplace of this is going to be e to the minus as. Because they're both the same function. They both have the same base function, just they have different shifts. And so I'm going to group together e to the minus as times inverse Laplace of 1 over s squared plus pi squared. Right? So once again, I'm taking the base function, I'm separating that from the shift, and then afterwards, after we apply the inverse Laplace to the base function, we're going to apply the shift to it afterwards. Okay? Okay, so inverse Laplace of 1 over s squared plus pi squared, this is going to be sine of pi times t. Okay. And then we have our shift. So we have e to the minus as to this. Okay. So let's do each of them individually. So first one we have, oh, I'm sorry. It's sine of pi t divided by pi. We need to divide by the frequency. Okay, so let's go ahead and shift this. And so our first term here has a shift of 1. Our second term has a shift of 2. And so we take these two. This is going to be 1 over pi. Let's do the shift of 1 first. So we have sine of pi t minus 1 times u of t minus 1. Okay. So this term right here is from that first shift of 1. Okay. And then second term here, it's going to be 1 over pi. This one has a shift of 2. So it's going to be sine of pi times t minus 2 times u of t minus 2. And this is coming from that second term. All right. Any questions on how we got this, how we got those two results there? Okay. All right, so now that that one's out of the way, let's go ahead and take care of this last term right here. So this last term actually has both an S shift and a T shift to it. Oh, question, can I go over that part again? Yeah, absolutely. So for this one, since these two terms here are essentially, they essentially have this, they have the same base function, right? And so the base function for both of these cases is 1 over s squared plus pi squared. It's just they have separate terms in our original functions because they're shifted by a different amount. And so the first term they were shifted by 1, the second term is shifted by 2. And so what I did here was I first took the inverse Laplace of that base function. Okay, so this 1 over pi sine of pi t, this is the inverse Laplace of the base function. Right, so ignoring any shifts that we have here, that's the inverse Laplace of that. And then after that, I applied the shift to that. Okay. And so because the first term here, this e to the minus s over s squared plus pi squared, that has a shift of just 1. And so that just becomes 1 over pi sine of pi times t minus 1 times u of t minus 1. So I basically replaced every t there with t minus 1. And I multiplied by the corresponding step function as well. And then the second term has a shift of 2. And so I have the exact same function, except I've shifted everything by 2. So every t is replaced with t minus 2. And then we multiply by the step function u of t minus 2. Cool, great. Okay, so then let's take that last term there. So this one has both an S shift and a T shift. So that last term there is e to the minus 3s going over s plus 2 quantity squared. Okay. So let's employ the same strategy for this one. So let's first take the Laplace transform of the base, inverse Laplace of the base function. Okay. So we're gonna have e to the minus 3s inverse Laplace of 1 over s plus 2 quantity squared. Because that we can do with just the table. Okay. So with this function right here, we have 1 over s plus 2 quantity squared. This s plus 2 that basically tells us that we have an s shift. Okay. So that means our inverse Laplace is going to have an exponential e to the minus 2t. All right, so first let me bring in the e to the minus 3s. Okay. So the s shift is telling us that we have an e to the minus 2t. Okay. Okay. And then besides that, we have inverse Laplace of 1 over s squared, which we know is the inverse Laplace of t, or the Laplace transform of t. Okay. All right, so that's our base function there. So our base function there with the s shift is e to the minus 2t times t. Okay. Now we're going to take this and we're going to apply our t shift on this. So remember, to apply the t shift, everywhere we see t, we're going to replace it with t minus 3 because we have an offset of 3 here. Okay. That means we're going to have e to the minus 2 times t minus 3, okay, multiplied by t minus 3, right? So t shows up twice here, so it appears both in the exponential as well as the kind of in front there as t by itself, okay? Then we're going to multiply this by the step function u of t minus 3. Okay. And so if we combine this together with the kind of what we got from the sine functions above, we combine it together with these two guys here, we just add them all up. And so that will be the Laplace transform of this, or the inverse Laplace transform of that entire expression. Okay. All right, any questions on this example here? Yeah.
What is the t minus 3 and the other, like the t minus 2 and t minus 1, what exactly do those terms do, like in the physical? I don't know how to say it.
Yeah, because no, it's it actually shifts them over to the right. And so, you know, for if you compare the functions t, so you have f of t is equal to t, right? This looks like just kind of a standard linear ramp, so it looks like this, right? But if you have the function f of t is equal to t minus 3 times u of t minus 3, what this is going to do is it's going to shift, it's just going to push everything to the right by 3. And so it's going to look something like this. So now this function is going to start at 3, and we have our linear ramp that kind of starts off just like.
So the t minus 3 has to be there so that the initial value is not wonky.
Exactly. Yeah. So that t minus 3 is there to make sure that the initial value is usually it's 0. Mm-hmm. Any other questions on this example here? Okay, so the next example that I have is actually solving a differential equation with all this stuff, and so hopefully I think once we solve this, it'll kind of make, you know, all this will kind of make more sense. Today was kind of one of those days where you kind of, you know, I kind of likened it, I kind of compare it to, you know, you're just starting a video game and they just throw all the controls at you and you don't really know where to use them all. So that's kind of what today probably feels like to you. But I think, once you start using these in equations and you see kind of the reason we have these shifts and the discontinuous functions, then I think hopefully it all kind of comes together from there. Now, I don't think we can finish this example. I think this will probably bleed over into Thursday. But I at least want to start it just so, we kind of hit the ground running on Thursday. Okay. So with this example, let's solve this ODE. Okay. So our ODE in this example is y double prime plus 4y is equal to a function g of t, okay, where g of t is going to be a discontinuous function. All right, so g of t in this case is going to be equal to 0 when t is less than 5. It's going to ramp up, so it's going to have a value of t minus 5 divided by 5 when t is between 5 and 10. Okay. And when t is greater than 10, then our forcing function g of t here is going to have a value of 1. Okay, so let's plot this out just so you can kind of see what it looks like. Okay, so the plot of this function is going to be 0 up until you reach a value of 5, right? Then what we have at this point is we have a linear ramp, and so it's going to ramp up just like this, okay? Until it reaches a value of 10. And at that point, it's just going to flatline into kind of a constant function. Okay. All right, so this function right here is actually quite common in kind of engineering practice. So this represents a situation where your forcing kind of ramps up slowly with time. And this is kind of pretty much the case for a lot of, mechanical systems, electrical systems, where, it takes a bit of time for it to kind of reach full power. And this kind of this equation and this function kind of helps to model that behavior. Okay, so eventually what we're going to do is we're going to solve for a solution to this ODE, but we're going to do it in a few different steps. Okay. Okay, so step one. Step one is to represent g of t using step functions. So kind of like what we did with the other discontinuous functions that we did examples of today. Okay. And then after that, we're going to take its Laplace transform. And what that's going to give us is g of s, big G of s. Okay. Right. So then we're going to have a Laplace representation of our discontinuous forcing function. Okay. Step 3. We are going to take the Laplace transform of the all the other terms in the differential equation. So pretty standard procedure from last week of taking a differential equation, taking its Laplace transform. Okay. Step 4 is we're going to solve. We're going to solve what we get in step 3 for big Y of s. Right, so that Y of s is going to include contributions from the differential equation. It's also going to include contributions from our discontinuous forcing G of s. Okay. And then once we have all that, step 5 is just to simply take the inverse Laplace of the entire thing. Okay, so that's our game plan. That's our game plan for this example. So, you know, I think we can probably do step one today, and then we'll finish up the rest of it. All right, so let's do step one. So let's take our discontinuous function here and represent it using step functions. Okay. So G of t. So G of t has kind of two parts to it. So there's a part where we have our linear ramp. So our linear ramp is t minus 5 divided by 5. Okay. This part of our step function here is activated at t is equal to 5. So we're going to take u of t minus 5. Okay. And this is deactivated at u of t minus 10. So we're going to subtract u of t minus 10. The other part of our step function, or the other part of our forcing function here is that we have a constant value of 1 that starts at t is equal to 10. So we have plus 1 times u of t minus 10. Okay. So that's step one. So step one is we took our forcing function. We kind of made note of every time each term is activated and deactivated, and we use step functions to represent that as one gigantic expression. Okay. So when we come back on Thursday, what we're going to do is we're going to first take the Laplace transform of this. We're going to apply our shifting theorems, and so our second shifting theorem, our modified second shifting theorem, is going to play a role here. Okay. And then we'll continue solving the entire ODE from there. Okay. All right. So thank you guys for coming today. I hope you guys have a good rest of your day, and I will see you on Thursday. Yeah, it did. Yeah, like learning a card game for the first time. Definitely, that's kind of what today felt like. Just a lot of rules, and a lot of things like that.
Can you tell me why you didn't solve like all these?
Yeah, it was just because I wanted to get to the ODE today, but yeah, in reality, what kind of this one's actually similar to that one. This one is the same thing except shifted by over 2, and this one is a cosine function. This one's actually very interesting. When you take the shift, you're going to end up with cosine of 2 plus pi over 2, which is actually just minus 1. Yeah. Yeah, so for that one, so we have this 1 over s squared plus pi squared. So this looks very similar to the Laplace transform of sine. And so if you look in the table, like we have sine of omega t, right? You take the Laplace transform. Its Laplace transform is omega over s squared plus omega.
Oh, yeah.
Yeah, so we're missing that omega up front. Yeah.
I got it.
Yeah.
I have a question.
Sure.
I was gonna ask you to write the entire, so for this one, so it's this times these, right?
Yeah.
Okay. Any way I can see like the full written out? For this?
For the entire.
Yeah,
Oh, so it's this plus this plus this. Because we basically take the inverse Laplace of each of these individually.
yeah.
So we did like this one first, which is this,
Mhm.
and then this one, which is this,
Mhm.
and then this one, which is this. So the
Oh,
final,
okay, that's what this is.
exactly, yeah.
So this is already this or?
No, this one is just the
It's
inverse
just, yeah,
Laplace.
that one.
This one right here.
Mhm.
So the full solution is just this plus this plus this. You just add them all up.
Okay. Can I still see like how?
Oh, yeah.
Sorry, and like.
It's this one right here. Mhm.
I don't know, but here's the thing, you say you have a positive there, here's negative, negative there. So even if that is a mess up on your part, like, we got the same thing